Okay, just give me a minute. Okay, so we're gonna do a couple of problems. Well, we're gonna finish the topic interference that we started Monday, and then we'll do a couple of problems for your exam. And if you have any questions, we can go through those. Okay?
I'm awake.
Are you okay with that? Okay. So let me see where we end up.
Everybody chicken farm.
Okay, so we finished last class, I think, around here. We were talking about Young's double slit experiment, and basically we were trying to set up the parameters to be able to solve these kind of problems. So again, what we are trying to do here is trying to find where on that screen, there is a distance L from our double slit, where on that screen do we have constructive and where do we have destructive interference? We're trying to figure out how that pattern of interference is being displayed. It's being displayed. What we need to do basically is we need to compare the difference in path between light coming from one aperture from the light coming from the second aperture. And we basically trying to find out this difference, R1 minus R2. And if that difference is a multiple of lambda, we're going to have constructive. And if it's a multiple of n plus 1/2 of lambda, then it's going to be destructive. That's basically what we're going to try to do. The problem is that these R1 and R2 are very similar to each other. So it's really hard to find that difference. So what we're going to do is use the small angle approximation and do a couple of tricks with geometry, trying to find out that difference. So we are assuming that we have this middle path that is right in between the two apertures. It's making an angle theta with the optical axis. And that theta, because the angles are very small, we can assume that they are kind of similar to each other. So what I'm going to do now, what I'm going to do now is I'm going to look very close to this area over here. So I'm just going to look at the aperture and the three paths of light coming out of here. So I'm going to do it somewhere else. So okay. Okay, so I have my two apertures. I know that there's going to be a distance d between the two of them. Okay, and I'm going to have light coming passing through those apertures. And again, the angles are so similar, especially if you see very, very close to those apertures, that you pretty much can pretend or you can assume that those beams are coming parallel to each other. So I'm going to have this light coming here. Okay, so again, this will be R1. This will be R2. And this will be just R. Okay, and this angle is theta. Okay, so what I want to find out is I want to find out how big R1 is compared to R2. So what I'm gonna do is imagine that I have a compass and I put one end on point P and the other one I put it here on R1, and I'm gonna trace that curve, and then I'm gonna find the intersection with R2. And let's say that the intersection is gonna be here. And I'm gonna draw a straight line from that intersection all the way to the first aperture. So it's gonna look something like this. Okay, if I do everything correct, I'm gonna have a 90-degree angle here. Okay, and this difference, this tiny difference, that's gonna be my delta R. This is gonna be the difference between the two paths. That's very convenient because I have a triangle rectangle. So I have a triangle rectangle. That's gonna look like this. This is my distance D. This is my delta R. And this angle over here is gonna be theta. Yes.
So what is delta R? I'm not following what you drew.
Delta R is the difference between R2 and R1. So
on your diagram, I get what delta R like represents for this. Did you draw a triangle?
yeah, so I have this triangle that is between the two slits.
Oh, okay.
And the intersection line between R1 and R2. Yeah, so now I can find delta R. So I'm gonna say, okay, this delta R is gonna be D times sine of theta. Yes? All good? And so now from here, I know that, okay, this is gonna be my distance delta R, and then this is what I need to compare to my conditions for constructive interference. So I can say that d sine of theta, if it's a multiple of lambda, then I'm gonna have constructive interference. Okay, if I want to evaluate the condition for destructive interference, then I will do d sine of theta equals m plus 1/2 of lambda. Now I'm gonna, because I'm working with such small angles, I can use a small angle approximation. And with a small angle approximation, I know that the sine of theta is very similar to theta. So I can say d times theta is going to be equals to m lambda. Okay, that still doesn't help me a lot. Like, I may be able to measure D. D is a couple of millimeters, so I may be able to measure D, but the angle is going to be super small, so that's not something that I can measure in a setup. The wavelength, well, if you're working with a laser, you may be able to find out what is that wavelength, but still, it's not something that is very yeah. So I'm still not done here. Remember, what I want to find out is where along this screen, I want to know if at this point P, if I have a constructive or destructive interference. That's what I want to find out. So I'm gonna add another term, and I'm gonna find the distance from the optical axis to point P. I'm gonna call that my distance y of m. Okay, I notice that here I have another really large triangle. So I have a triangle with one side L, the opposite side y of m, and at an angle theta. Okay, so I'm gonna draw it over here. Okay, and from this triangle, I can say, well, tangent of theta is going to be equals to y of m times L, or 1 of m is going to be L tangent of theta. Okay, now again, we're working with a small angle approximation. So if I were to look at tangent of theta, well, tangent of theta is the same as sine of theta over cosine of theta. Using small angle approximation, I know that sine of theta is going to be theta, and cosine of theta will be very close to 1. So with a small angle approximation, I can say that tangent of theta is very similar to theta. Which is convenient because I already have another expression that involves theta. So the d times theta is equals to m lambda. Theta will be m lambda over d. And from here, I can say that y of m is going to be a L m lambda over d. And this will be my condition constructive interference at a distance y from the optical axis. Yes.
Can you go back to where you got the triangle that you drew with the L and the Y sub M?
This one?
Yeah, from like the original.
This one over here. So the triangle is between the red line the optical axis, and wire length. Yep. Yeah, makes sense. So here's the interesting thing. Like, so remember, we have our optical axis, and we're trying to find out where are we going to have a bright fringe or dark fringe. Okay, we can have them above the optical axis, but we can also have them below the optical axis. So y of m can also be negative. Now, L is a distance, so that's going to be positive. Lambda is a wavelength, so that's going to be positive. And D is the distance between the apertures. So the only way we can have negative y of m is if m is negative. So before we've been talking about m's to be integers. In the case of standing waves, it's only going to be positive. But when we are talking about interference, m can be positive and negative. So here we can have m equals 1, 2, 3, and we can have m equals 0, and then we can have -2, -3, and so on. So at these points, you're going to have a bright fringe on your interference pattern. Okay. Now notice that regardless of wavelength, regardless of the distance between on your slits, regardless of anything, at m equals 0, so along the optical axis, you're always going to have a bright fringe. Okay. And again, these m's are usually called orders. So you're going to see it as orders or modes. So if I'm talking about the third constructive mode, or the third constructive order, they basically imply what happens when m equals 3. If they say what is the fourth constructive order, they implied m equals 4. Just give me a minute. Okay, any questions? Okay. Now, interference patterns are usually one of the things that we want to measure. Like if you look at this equation over here, the distance y is something that you can actually measure in the lab. Like you can have your interference pattern on a wall and you can measure the distance to a positive or negative fringe. You can measure the distance L, that's basically the distance from the double slits to the viewing screen. And you probably know the distance between the two slits. So one of the reasons that we care about working with interference is that we can find the value of lambda. We can find with very accurate, we try to find out what is the wavelength of light that you are working. Different values of wavelength, so different values of light, whether you're working with blue light or red light, they're going to give you different values of y. So when you have interference with white light, usually what happens is that it's going to split and it's going to create kind of like a rainbow. And then you can make measurements with blue lights, red lights, and so on. And we're gonna see that this is used for spectrometers later on. Okay, so we'll do a very quick example. So let's say that we have a double slit experiment. We have that the spacing between the slits is 0.2 millimeters. And the distance to the viewing screen I'm gonna say that is 1.5 meters. Okay, and I'm gonna measure the distance from the center to, and I'm gonna count 10 positive fringes. Or the distance between 10 constructive or bright fringes is 3 centimeters. Okay, and I want to know what is the wavelength of light. Yeah, Mary?
What is where it says, I don't have my glasses. I can't see.
Which one?
The middle one?
This one?
Yeah.
The distance between 10 bright fringes is 3 centimeters. Okay, so a couple of things here. I'm gonna, I know that the distance from the optical axis to one of the fringes, to the first bright fringe is gonna be given by this equation. Y of m is gonna be L lambda, Lm lambda over D. Okay, now the next bright fringe, okay, is gonna be y of m plus 1. So regardless of the value of m, the next one is gonna be m plus 1. So this one is gonna be at a distance L m plus 1 lambda over D. So the only thing that I'm doing is just changing that value of m. So if I'm looking at the third fringe, the next one is gonna be the fourth fringe, and so on. So now I want to see what is the spacing in between the two of them. So what I'm gonna do is I'm just gonna subtract. I'm gonna subtract y of m plus 1 minus y of m. I just want to know what is the spacing in between. So for the first one, I'm gonna expand this, and I'm gonna have Lm lambda over D plus L lambda over D. And then I'm gonna subtract y of n, which is L m lambda over D. And you can see here that these two guys are gonna cancel. So the spacing between two fringes Well, between two consecutive with Q, with no. Fringes. Holy crap. Okay, so it's always going to be that. Every time you have two consecutive fringes, two consecutive bright fringes, or two consecutive dark fringes, the spacing is going to be L lambda over T. Okay. So to solve this problem, well, we know the spacing between these slits is going to be 0.2 millimeters. Bless you. So this is going to be 0.2 millimeters, or 0.2 times 10 to the minus 3 meters. L is going to be 1.5 meters. And I know that 10 consecutive fringes, so 10 times delta y, is going to be equals to 3 centimeters. So delta y is going to be equals to 0.3 centimeters. So this is going to be 0.3 times 10 to the minus 2 meters. Okay, so there you go. Try to solve this one. Okay. Okay, I think everybody got 4 something, either 400 nanometers, some of you got all the way to 4 nanometers. So we agree on the value, like a 4, we don't agree on the exponent. So I'm gonna try to solve it really quick. So I know delta y to be 0.3 times 10 to the minus 2 meters. And I'm gonna be solving here for lambda. So lambda is gonna be d times delta y over the distance. So this will be 0.2 times 10 to the minus 3 times 0.3 times 10 to the minus 2 over 1.5. And I think that should be, it should give you 400 nanometers. 0.2, 0.3, oops. Yeah, so that is 4 times 10 to the minus 7. This is 400 nanometers. Yeah. So if you got something different, double check your exponents. Make sure that you have everything in meters. Probably there was something there that you missed multiplying. Okay. Makes sense? Pretty straightforward. We'll do one more really quick. Okay, we have again a double slit experiment. We have a source of light with a wavelength of 500 nanometers. And it's illuminating a double slit. And the fringes, the first fringe or the fringes on the screen are separated a distance of 4 millimeters. The screen is 160 centimeters away. And what I want to find out is what is the distance between the slits. By the way, I had the grades for your first two labs. I already put them on Canvas. If for some reason you couldn't do one of the labs, I mark it as a 0, but as soon as you do your exam, as soon as you do your lab, I will update your grade. So don't worry so much about that. Okay, I put the 0 so that you can actually see the current grade instead of, if you don't put anything, then it just counts the grades that are marked. So it gives you inflated grades. So. Oops. Okay, so I know that delta y is going to be L lambda over D. I'm trying to find the distance D between the two of them, or between the two slits. So I'm going to have L lambda over delta y. And from here, I just need to substitute some values. So I'm going to have 1.6 meters times 500 times 10 to the minus 9. That's nanometers. Divided by delta y, which is 4 times 10 to the minus 3. And Cameron, what you got?
Mine was wrong.
What's wrong?
Mine was wrong. I put 0.16 instead of 1.6.
Uh-uh. So never mind. Times 2. 500. And I got 20 times 10 to the minus 6 meters. So 20 micrometers. Yeah? Everybody got that?
I'm good.
2 times 10 to the minus 6.
I could.
I got 2 times 10 to the negative.
Yeah, it's hard.
Oh. Sorry. 2 times 10 to the negative 4 meters. Okay, so that's 200 nanometers, 200 micrometers. Yeah. Is 200 micrometers. Okay, makes sense? Okay, so I'm gonna stop here with interference. Do you guys have any questions about your exam? Is there any topic that you want me to go through? Any concept you want me to repeat? Yes.
So just to clarify, is any of the double slit kind of stuff gonna be on the exam or no?
No. Yes.
Can you just go over again what's going to be on the exam?
Basically, it's going to be chapter 14, 15, and 16. So it's standing wave, simple harmonic oscillator, and superpositional waves. The oscillations. The traveling waves and standing waves. Nothing? Everything clear? Perfect? Yes.
Can we do a problem from chapter 15?
Chapter 15.
Yeah,
Okay.
like a frequency shift problem.
What are the Doppler effect?
Yeah.
Sure. Do you want the two of them moving or just one moving?
Probably both moving.
Okay, those are more difficult. Okay, so I'm gonna assume that we have that. And I'm gonna say that this bat is emitting a frequency of 25 kilohertz. It's moving at a velocity of 30 meters per second. Okay, and it's gonna be chasing a moth. That is traveling at a velocity of 15 meters per second. And they're chasing each other. Okay, so the bat is sending chirps of sound and it's just receiving the echo. So one thing I want to find out is, okay, the bat is receiving the echo. Two point 5 seconds. No, I'm gonna say well, 2.5 seconds after sending a signal. Okay, so I want to know what is the distance to the moth. And the second question will be, what is the shift in frequency? Received by the moth. Okay, give it a try. Try to solve those two. So for the first part, I want the echo. So the signal is going to the moth, bounce back, and get back to the bat. So I want to know, based on that delay, how far is the moth? And for the second part, I just want to know what is the frequency received by the moth. showing here, you can assume that the speed of sound is 340 meters per second. All right, Fox. I went to the
My
gym.
legs,
Yeah, I went to the gym for the first time. I don't know how long. I just threw.
my sore too.
Yeah.
Not all that.
So.
So I'm not looking at the bounce back. I'm just the one like the month. If I were asking the shift in frequency and the echo, then just.
Okay. So for the first part, I have to find. I know if he's velocity to find distance over time, but.
So the speed of sound is going to be the same, so it's not going to change. It's going to have the 240 meters per second. So you have something flying at that velocity, and it takes 2.5 seconds, half of that to reach the band, and then half of that to get back. That's 2.5? 2.5, sorry, I did. So it's going to be half of 2.5 to get to the back, to the mouth, and half of that come back.
Did you see it, that's cool?
That's why I asked you, because I can see the dots. That's why I asked. Yeah, that's a big space in between the.
So I enjoy the sound of it.
In the big space.
The velocity sound, because it's the sound wave that is traveling.
Yeah, you did 25 too.
No, I didn't, I said 2.5,
So like,
no, I used.
I think we can set that there.
Because I used 343.
It's the opposite way.
Because that was already
So I just have this is 2 instead of the times 1 half. So I did the same, I got the same, so I did.
Yeah, I think that math works. So for the first part, okay, first it's 2.5 seconds. It's 2.5 seconds, not 25. And basically, as you can imagine, you have the bat, and the sound takes 2.5 seconds to do the round trip. So it's going to be 2.5 divided by 2 is what, 1.25? 1.25 seconds to go up and 1.25 seconds to go down. So we know that velocity is distance divided by time. So the distance will be just velocity multiplied by time. This will be the speed of sound. That's the pulse of sound that is traveling, that is taking that time to travel, multiplied by 1.25. Okay, so this will give you it will give you 425 meters. If you use 343, is 428 0.75 meters. Okay, so what you did was multiply by 2, right?
Yeah.
So, okay, this is just a small parenthesis. So I have distance divided by the time that it takes me to travel divided by 2. Okay, and if I work a little bit with the algebra here, this is going to be the same as 2d over t. So you're going to get the same answer.
All right.
Okay, so it just works that way. Okay, for the second part, I just want to know what is the shifted frequency on the moth, not on the way back. Okay, so I need to do just one pass of Doppler effect. So I'm gonna go with the general equation. So I know that the shifting frequency, so the frequency on the observer is gonna be given by V plus minus V naught over Fs. Let me double check. Just to make sure that I have that equation correct. Nope, I was getting wrong. It's BO BS. Okay. So I'm gonna try to find out what sign do I use in the denominator. So I'm gonna assume that the observer is static. The bat is getting closer to the observer. The frequency is going up, so this sign is gonna be negative. Trying to find out what sign do I have in the numerator. I'm gonna ignore the velocity of the source. The moth is moving away, so the frequency has to go down. So this will be -2. So that's the equation that I'm gonna be using. And from there, I can just substitute values. And does anyone has an answer?
26.2 kilohertz.
26.2
Kilohertz.
kilohertz. There you go. Okay. Yeah, makes sense. Okay, now this is the problems that this kind of problems. I think many of you still are a little bit confused. So I have a string on a a mass on a spring, and this thing is oscillating. Okay, I know that, and let's say that the equilibrium point is somewhere around here. I know that when this mass is displaced 5 centimeters, is displaced 5 centimeters from the equilibrium point, the velocity of the mass is 3 meters per second. Okay, I want to know what's the velocity when the displacement is 6 centimeters. Anyone has an idea how to solve this problem? Andrea? No? Cristina? Okay, yes.
I have an idea, like, I don't know how to like explain it, but I have an idea of how to solve it.
Like, walk me through your idea.
I guess I gotta find, we did one like this. Way back.
We have done a couple of that. So one of the things that you need to remember is that the energy on the whole system is going to be conserved. So you find the energy at one particular point, you can find that energy is going to be the same everywhere. Yes.
You just set up the energy equations with the elastic potential and the kinetic energy.
Yep. So I'm going to have that the total energy is going to be kinetic energy plus potential energy. So this will be 1/2 of the mass velocity square plus 1/2 of k. Oh, I will need to give you k. Let's say that k is 200 newtons per meter. 1/2 of k delta x square. Okay, so on your first step, you know that the velocity is going to be 3 meters per second, and you know that delta x is going to be 5 centimeters. I have to write in meters. So using these two, I can calculate the total energy. Okay, and that total energy is going to remain constant. So then for the second part, to calculate this one, then what I need to do is the total energy is going to be conserved, so the total energy, and now the displacement is going to change. So I'm going to use the same equation, but now in this case, I know the total energy, which is going to be whatever I got from here, and I know delta x, which is going to be 0.06 meters, and then I calculate for the velocity. Yes.
Do we need the mass?
Yes, sure. You can also need the mass. So the mass is going to be 2 kilograms. Okay, if I were to ask you for the maximum amplitude, well, same thing. I know the total energy. I know that the total energy is going to be 1/2 of k. The square or the maximum amplitude. So I know the total energy, again from here, and I can calculate the maximum amplitude. And if I were to ask you what is the total velocity, the maximum velocity, same thing. You know the total energy, and this is going to be Vmax squared. What you that you can never do is this. You cannot do that. You cannot do in the same equation, put the maximum amplitude and the maximum velocity. This will give you twice the energy that you have in the system. So just be careful. This is the most common error that I see. Okay. Okay. Any questions? Okay. So let's stop here. If you have any questions about the exam, send me an email. If you need special accommodations, send me an email. If you just want to say hello, send me an email. Have a good day. See you Friday.